Ladies and gentlemen, today we are going to be talking about populations. How many individuals are in a particular group? What happens if there's too many of them? How do we prevent it from becoming too many? Well, as my good friend Chucky D over here, Charles Darwin, he said there is no exception to the rule that every organic being naturally increases at so high a rate that, if not destroyed, the earth would soon be covered by the progeny descendants of a single pair. What does that mean? It means if nothing stops the species from growing, they will overpopulate the world. Right? If there isn't something to stop a population from getting more and more and more kids, there'll be way too many and not enough resources. We can actually measure that. We call that a J curve. If you look at this chart right here, we have generations, just like a lab that you guys have done recently, the breeding bunnies. Every generation you measured how the gene pool changed. But this time we're not measuring alleles, we are measuring numbers of individuals. So every line is 10,000, we'll say people, 10,000 people. And then 20,000, 30,000, 40,000, 50,000, 60,000 people. And you can see over the course of generations, we are going to see that they are growing exponentially. How a population grow if nothing stops it? It will grow exponentially. What does that mean? There's that word there. It means it will be like twice the previous amount. So if we had, I don't know, 10 people, next generation, we could have 20 people because that's doubled the previous one. And then 40. Yeah, we didn't go 10, 20, 30. We went 10, 20, 40 because we're doubling. And the next generation would be all the way up to 80. 10, 20, 40, 80. And then the next will be 160. You see what's going on here. 320 after that. It is getting way too big. And it's getting way too big too fast. So after a while, we see the growth jump. So it took 8.5 generations to get 5,000 people. And only half a generation, like half that time of one generation to get the next 5,000. Look at that. 8 generations to get halfway up, and then 1 generation to get the next half. And then a full 1 generation to go a full jump. Not even half, fully. Next generation, it went up 2. So it went from, well, in that case, 20,000 people. That's called a J curve because the exponential growth, the doubling every generation, is going to cause this J-shaped curve. And the more populated you get, the next generation will increase by a multiple of the previous generation. That's what I'm saying. It's doubling every time. Doubles the previous one. And every generation, this line gets steeper and steeper until eventually it's going to be a straight line up. And at that point, there is nothing we can do to stop it. It's just way too overpopulated. The environment cannot support us. Luckily, in most cases, we have something called a carrying capacity. As population grows, it is going to use more and more and more resources. And the death rate is going to increase because as we're using those resources, we are running out of food, we are running out of water, we are running out of shelter, we're running out of space. So we have to fight each other for it. That's what it means to compete. We're racing to get to the food first. And whoever eats is going to be, there's going to be someone else who doesn't eat. Every time someone gets a drink, there's going to be someone who doesn't get a drink. And that's what I mean by competing. And those people who aren't getting the resources are going to die. And the birth rate is going to decrease. What does that mean? Why? It means we're going to have less babies. How come? Because people are dying. If people are dying, they're not reproducing. So we're going to have less babies. And even if you do have a baby, that baby needs resources to grow. Pregnant women need a lot more resources for the baby. Babies who are born need a lot of resources. So eventually, we don't have any room at all. When the amount of births balances out and equals the amount of deaths in a population, for every giraffe here born, another giraffe dies, that is when you have hit carrying capacity. And the population stops growing. So that is when this J curve stops going vertical and goes horizontal again. Then J curve rises exponentially, and then we run out of resources, we run out of room, we run out of everything. Oops, there were still words there. As time progresses, the organisms can't maintain the numbers, not enough resources. So we start balancing out. Something starts causing whatever population we're talking about. Giraffes, something's going to start causing those giraffes to die. We're talking about people, something's going to start causing people to die. And they're going to stop rising. So this dotted line represents a point where we cannot cross. I'm not saying we're not allowed to cross it. I mean, we are not capable of crossing it. If we try to go any higher than this line, instead of crossing it, people will die. So that's why we balance out. Oops. The population can never exceed the carrying capacity. Now, here's the cool thing, though. We can raise the carrying capacity. We can take this dotted line and find a way to rise it up. And that's what we as humans do all the time. Right now, let's talk about what's happening in the world, COVID-19, right? That is something that is happening because we are reaching our carrying capacity. We don't have enough resources to go around. We don't have a resource we need for this would be space. We need space to spread out away from each other. And we don't have a lot of it. We're overpopulated. We can't really, it's hard to get away from each other and survive. We're struggling right now trying to stay away from each other and still get along with our daily lives. So we have no choice but to be near each other if we're doing things. So we're spreading the disease. And people, unfortunately, are dying because we are at carrying capacity. So what did we do? We created vaccines. We made masks. We made rules about social distancing. What we did was change our environment. And when we change our environment, we can raise the carrying capacity. And that's what we're trying to do. And that's what we've been doing for years. We built the railroad. We changed our carrying capacity because we can move resources around. We invented airplanes. We invented clothing even before all that stuff. We invented refrigeration to keep our resources around longer. So all of that stuff kept raising our carrying capacity until we overpopulated. And now we're at it again. So now we're trying to raise it again with medicine, vaccines. So question is that a good thing or a bad thing? That's up to you. I'm not going to tell you that. Now, there are some things that are going to cause us to hit that carrying capacity, like that COVID-19 we just talked about. That virus is a limiting factor, something that is going to stop the growth or abundance of an organism or population. Something's going to prevent us from increasing our numbers. Maybe you ran out of food, maybe you ran out of clothing, maybe you ran out of space. In this case, viruses will be a limiting factor, something that's keeping our numbers from growing. This is what creates the carrying capacity to begin with. It's also known as environmental resistance. We resist the growth of a population, or we don't, they do. Whatever it is that's affecting us and preventing our population from growing is going to prevent us from, they are resisting our growth. And there are two kinds of limiting factors. Two types of things that are going to prevent our numbers from getting bigger, prevent our group from growing. They are called density dependent limiting factors and density independent limiting factors. So what does that mean? Density dependent, to depend on something, means we require it to work. So density dependent means we have to be packed in really tight. We got to be overcrowded for this limiting factor to hurt us. And density independent means it doesn't care how packed in we are. Whatever this limiting factor is, it's going to hurt us if we're close together or far away, whatever. It doesn't matter. It's going to hurt us. So let's look at some examples. Density dependent. Limiting factors where large, dense populations are affected more than the small, less crowded ones. The more of us are in a location, the more it's going to hurt us. For example, food and water is a density dependent limiting factor. We have a limited supply. We don't have enough food to go around, so we are going to have to compete for it. So the more of us that there are in this location, the more competition there's going to be. So here, instead of us, let's look at these cows. I didn't feel like animating a bunch of people dying, so I'm better okay with I'd rather use cows. Better okay. I gotta learn my English. So we get more cows, and look what happened. We got plenty of water in this little area. We got plenty of vegetation for them to eat. But if we get more cows, they end up eating more food and drinking more water. Now they're starting to run out. Do you see what's happening here, guys? The denser the population is, the worse it's going to get until eventually there's not enough food to go around, not enough water to go around. And, animals start dying because they died of starvation or died of thirst. So food and water are density dependent limiting factors. They will keep the animals at the carrying capacity. They can't get any higher than this without dying. Another example is living space. The less space there is, the less room for the people or plants to grow. So I'm using plants for this example. Plenty of sunlight to go around, right, for these three little plants growing, but as they get bigger, they're going to need more space. And unfortunately, this little guy in the middle isn't getting enough sunlight because these two guys around it are taking up the resources. They're blocking the sunlight. So eventually, this little guy in the middle is going to die because it didn't have enough room to grow. So now we have left living space. Let's go back to that food web idea we had. We now have less plants and therefore less food for the animals. So there now less space equals less food. That's a combination of limiting factors. Another limiting factor, predation. Predators, animals that want to eat other animals. The more prey there are in an area, in this case, there's a lot of cows just hanging out here. That's like ringing the dinner bell, guys. These wolves or whatever would be in this area are going to hang out in this area. Why? Because there's plenty of food. They're not going to go hang out where there's not that much food. So the more animals there are in one place, the more predators there will be, keeping the population down. And to go back to a previous example that I talked about, disease. Spread of disease is faster in denser populations. So for the example I used before was COVID-19, right? I actually made this animation before COVID-19 was even a thing. I'm using an old animation, but it still works. So this pink animal represents a diseased animal, someone with the disease, COVID-19 in this case. I don't think it affects cows, but let's go with it. It's a disease in general. And within the 6 foot radius, this is bigger than 6 feet, but I just wanted you to see it. Within the 6 foot radius, you can spread the disease. This is the area that it is contagious. And so this guy will spread to the ones around him. This one will spread to the ones around him. The bigger, denser the population is, the harder it is to stay away from that area. And the more it's going to spread. And that's what happened to us with COVID. We got so overpopulated, us humans, across the whole world that when COVID-19 came out, it spread across the entire planet like wildfire because there was just not enough room for us to get away from it. So while you guys are now losing sleep over thinking maybe COVID-19 might be a good thing for the environment, is that what Laconia just said? No, I don't want to say that. I'm not. Not good for anyone who has it, but you know, if it lowers the population, isn't that technically healthier for the population? I that's something you can lose sleep over. I don't want to be the one to tell you that either. That I'm going to let you guys come up with that answer on your own. But while you're losing sleep over that, let's talk about the next thing: density independent limiting factors. Limiting factors that affect populations regardless of size. I mean, it doesn't matter if we're overpopulated or not, right? We could have 3 individuals, we can have 3 million individuals. These kind of limiting factors will hurt us the exact same way regardless. Now, what could do that? Examples would be pollution. You know, it can poison, something can poison a small group or a large group. You know, if the water is poisoned, it doesn't matter if there's only 4 cows drinking out of it or 40 cows drinking out of it. You know, they're all drinking poisoned water. Another example is uh, earthquakes or other kind of natural disasters around them, right? It doesn't matter if there's 4 cows or 40 cows and an earthquake hits, that whole area is getting affected. Temperature. You know, if it gets hot, it just gets hot. It doesn't matter how many there are. You know, you can die of heat stroke. Or, you know, weather in the opposite direction, snow, sleet, hail, whatever, preventing plants from growing, preventing you from getting warm, freezing to death. You know, these are all density independent. Oh, I just made the water freeze over, so now they don't even have easy access to drinking water. So those are all the various things that could prevent a population from growing. So think about that next time you do anything that can affect the environment. You want to drive a car and put carbon dioxide into the air, we know that's going to increase the temperature of the planet. That's just a proven fact. And temperature is density independent. You know, you want to go shopping for way more food than you really need and end up wasting it because it went bad before you ate it. Well, that's someone else who didn't eat. So think about all those actions and how it's going to affect the overall population. We live together. It's not just you and your family, it's everyone in the whole area. All right. So while you are thinking about that and mulling it all over, I am going to go and I will see you in class next time. Have a good day, guys.